Hey everyone, welcome to the Explainer. If you're gearing up for a big technical interview, or maybe you just really want to bulletproof your Java foundation, you are exactly where you need to be. Today, our mission is to completely master these core Java interview concepts. And we're not just going to sit here and memorize textbook definitions, right? We're diving into the entire journey of Java code, from that very first architectural blueprint all the way down to how it actually executes in memory.
So, here's our game plan to logically conquer these concepts. We're gonna hit 1. Java architecture and basics. 2. The pillars of OOP. 3. Core mechanics and keywords. 4. Understanding Java strings. And 5. Exceptions and memory management. Let's jump right in.
Section 1. Java architecture and basics.
You've probably heard the phrase, write once, run anywhere. It's literally the core philosophy of Java. When you write your Java source code, it gets compiled into this beautifully platform-independent bytecode. So as long as the system has a Java virtual machine, a JVM installed, it can read and run that code. Windows, Mac, Linux, honestly, it doesn't matter. It's a truly universal language.
Now, a massive, absolutely classic interview staple is explaining the difference between the JVM, JRE, and JDK. Think of them like Russian nesting dolls. At the very center, you've got the JVM. Its one and only job is executing that bytecode we just talked about. Step 1 layer out, and you hit the JRE. That contains the JVM, plus all the core libraries you actually need to run applications. Then, the outermost doll is the JDK. This is the whole shebang. It has everything from the JRE plus your development tools, like compilers and debuggers. The easiest way to remember it? You need the JDK to write the code, but you only need the JRE to run it.
Moving on to Section 2, the pillars of OOP.
First up is encapsulation. This is all about wrapping your data and methods together into a single, cohesive unit. It's basically about protection. Imagine you've got an employee class. You definitely do not want some random part of your program going in and directly altering an employee's salary. So you make that data private. You restrict access using modifiers. Essentially, you're throwing a protective shield around your most sensitive data. Next, we've got inheritance. This lets one class acquire the properties and methods of another class. It's honestly the ultimate shortcut for code reuse. If you have a parent class named Animal that has an eat method, you can easily create a child class called Dog that just extends it. Boom! Suddenly, your dog class already knows exactly how to eat, and you didn't have to rewrite a single line of code. Pretty great, right?
Our third pillar is polymorphism, which literally translates to many forms. This is what gives our code its incredible flexibility, allowing one interface to have multiple different implementations. And this happens in 2 distinct ways, compile time and runtime. Definitely keep those 2 concepts in your back pocket, because we're going to break down exactly how they differ in just a second.
But before we do, let's hit our final pillar, abstraction. Abstraction lets you use a complex system without needing to understand the messy internal engine making it run. By using abstract classes or interfaces, you hide all those complicated implementation details. But here's the key distinction interviewers want to hear. An abstract class can hold state and have constructors, whereas an interface is purely for defining capabilities, and it actually supports multiple inheritance.
All right, Section 3, core mechanics and keywords.
So, remember polymorphism from a minute ago. This is exactly where interviewers love to set a trap. You've got to know the difference between overloading and overriding. Overloading happens within the same class. It's compile-time polymorphism, where your methods share the same name, but they take different parameters. Overriding, on the other hand, is runtime polymorphism. That requires a parent-child relationship, where the child class provides a custom, updated implementation of a method that has the exact same signature as the parent.
You're also going to want to nail down 3 core keywords. First, constructors. These are special methods with no return type, and they're used purely to initialize new objects. Next up is static. If something is static, it belongs to the class itself, not to any specific object instance. And finally, final. Think of final as a padlock. A final variable cannot change its value, a final method cannot be overridden, and a final class cannot be inherited. It's all about enforcing strict behavioral rules.
Let's pivot to Section 4, understanding Java strings.
Strings are arguably the most heavily tested objects in any Java interview, and here's a classic example of why. Listen closely. Never, ever use the double equals sign to check if 2 different string objects contain the same text. Why? Because double equals only compares their memory references. You could have 2 totally different objects that both contain the word Java, and double equals is going to look at them and say false. If you want to check the actual text content, you absolutely must use the dot equals method.
Which leads to the notorious question, why are strings immutable? Why can't you just change a string object once you've created it? This question is designed to test your deep understanding of Java's underlying architecture. The big three answers here are security, thread safety, and memory optimization. Because strings never ever change, Java can safely cache them in a string pool to save on memory. Plus, multiple threads can share the exact same string without any fear of accidental data corruption.
Okay, but what if you do need to constantly manipulate text? Creating a brand new, immutable string every single time is going to be incredibly inefficient. That's when you bring in the heavy hitters. You've got String Builder, which is mutable and blazing fast, but it's not thread safe. And then you have String Buffer, which is mutable and thread safe, but that extra safety makes it a bit slower. The interviewer wants to see that you can pick the perfect tool for your specific performance scenario.
And finally, Section 5, Exceptions and Memory Management. Now, to handle runtime errors gracefully, we rely on try, catch, and finally blocks. But the real test here is knowing checked versus unchecked exceptions. Checked exceptions, like an I/O exception, are caught at compile time. The compiler is basically acting like a super strict boss here. It literally refuses to build your code until you handle the issue. Unchecked exceptions, like the dreaded null pointer exception, happen at runtime. Those are the sudden, nasty surprises you have to try and anticipate as a developer. Diving under the hood, the JVM divides its memory up into a few specific areas. But the real star of the show is the heap. The heap is where all your objects live, and it is heavily monitored by garbage collection. You can think of garbage collection as this built-in robotic maid. It automatically sweeps through the JVM, finds all the old objects your program isn't using anymore, and literally tosses them in the trash. It keeps your memory running super efficiently, and you don't even have to lift a finger to clean it up.
All right, let's pull this all together and look at the complete life cycle of a Java program. Step 1, your source code gets compiled into that platform-independent bytecode. Step 2, the JVM loads up those classes. Step 3, the verifier steps in to check the code for any security issues. Step 4, the execution engine and the JIT compiler run the code for maximum performance. And finally, Step 5, that garbage collector runs quietly in the background, keeping your memory spotless. So, from the initial architectural blueprint right down to memory execution, you've now got the framework you need to completely ace these concepts. The only question left is, which of these internal JVM systems are you going to dive in and master before your next big interview?